All right, so today's screencast, I'm going to be talking to you folks about the nature of gases. Now, I realize things are a little bit backwards because we did a lab about gas laws before I even introduced the concept of gases, but sometimes that's a really good idea because it forces you to explore things that you don't really understand rather than fitting an idea into something you've already seen, which is usually less exciting. So we're going to be talking about the nature of gases, and in some ways this is going to help you to understand what we did in lab the other day a little bit better. So, first things. One, gases have mass. Now, this may be sort of obvious, but it isn't always an obvious thing. So, if you take a look at this, we have a balloon here that's deflated on this side, and we have a balloon here, the exact same balloon, that's inflated on this side. And you can see, obviously, that this scale, this balance, is tipped a little bit down relative to up over here, indicating that whatever's inside the balloon has enough mass to actually cause this tipping. Okay? So, despite the fact that in the most cases, air or gases are incredibly light, they still do have mass. Second thing here is that gases are compressible. And if you look here at this figure, don't forget that gases are, there's a lot of space that exists among all the particles that make up a gas, which is why we can always say that 22.4 liters of a gas at STP is going to be 1 mole of that gas, because the actual volume of the gas particle itself is meaningless. Okay, so you can see here, as a result of having so much space around the particles that make up the gas, they're compressible. You can actually push them closer to one another. They're not going to like it, but they will be pushed closer to one another. And then if you lift it up, you would obviously lift it up on this side over here. Whoops. On this side right here, you can imagine that the molecules, the particles of the gases are going to bounce around and push that piston back upwards, not unlike what you did in lab the other day. Okay, number 3. Gases fill their containers completely. Okay, and you can see with this diagram, which is comparing the 3 different states, gas, liquid, and solid, that in the case of the gas, they're all the same exact container, but in the case of the gas will actually move around and entirely fill the container, whereas the liquid will stay in a portion of it, and then the solid stays in even a smaller area of that container. Okay, so clearly gases, in this case, you already understand that concept probably without even realizing it. It's not like you can go to one portion of the room that you're sitting in and it's a vacuum where there's no gas, because the gases completely fill the area of the volume of the entire room. Okay, so for number 4, gases diffuse easily through each other. And you can see here in this schematic here, I have a whole bunch of these red dudes that are hanging out here, and after time they start to move out and diffuse throughout the entire set of particles, so that they're found throughout and among these other orange gas particles. Okay, so that's the nature of gases, and that's going to be an important thing for one of the gas laws that we'll be talking about later. And number 5, gases exert pressure. And in this schematic, what I'm showing is that the gas particles, the pink guys, are moving around rapidly, and when they hit the sides of the walls of a container, they actually push. It's a small force, but collectively it's a large force against the inside of the container. And that pressure, which is the force per unit area, means that the gases exert pressure. And then lastly, number 6, temperature will impact the pressure and the volume of a given amount of gas. Now, this is what we did in lab the other day. Of course, this was the second part of the lab that kind of failed us miserably. But you could at least see through the graph that I had you guys take a photo of that when you increase the temperature of a given volume of gas and you don't change the volume, that will increase the pressure of that gas. Or if you were to increase the temperature of a given volume of gas, but you would allow that volume to expand if it wanted to, and kept the pressure the same, then the volume would increase. It would go up in size. So that's something we're going to be talking about with the gas laws. But you certainly had some level of familiarity with it in lab this past Thursday. So let's talk about this concept of pressure. As I just mentioned before, pressure is the force per unit area. But let's bring this to something that you're more familiar with, which is the concept of atmospheric pressure. Why is it that there is pressure in the atmosphere when we basically have a giant size open container, everything around us? It's not like we're sitting inside of a small room and they're pumping air into us and it's making our ears pop. Well, the reality is we sort of are. The entire atmosphere that surrounds the Earth is still a fixed volume. It's a huge volume, but it's a fixed volume. And you can imagine, if you look at this schematic that I have here, if you were to create a column of air that was 1 meter by 1 meter, and that was the entire thickness of the atmosphere, as you can see that's been done here, all that mass that I was talking about, all the mass of the air particles that are in that column, gravity pulls them down. So they have a mass that pulls them down. And if you're standing in that 1 meter by 1 meter area, you feel that pressure. Now, you're so used to it, you don't really feel it because it's part of your existence on Earth. You've never not had this situation unless you're somebody who's climbed to the top of Mount Everest, for example, where the column of air above your head is much shorter, so it's not going to be as heavy. But what's important for us to see here is what I have right here. The pressure exerted by the atmosphere on a 1 square meter area of the Earth has a certain power to it, or a certain pressure, and we call that 1 atmosphere of pressure. Okay, now that's going to be an important thing to take home. We've already talked about the concept of atmospheres, or ATMs. So let's see where else this takes us. 1 ATM, 1 atmosphere, is equivalent to 760 millimeters of mercury. And you might ask yourself, what the heck? That's weird. That doesn't make a lot of sense. You'll see in a moment where that comes from. And that is also equivalent to 101,325 pascals. And if there are 1,000 pascals in a kilopascal, that also means there's 101.3 kilopascals equivalent. All right, so those are all, oh, and by the way, you should know that going back to physics, that a pascal is equivalent to the number of newtons per meter squared. Okay, so that goes back to the whole meter squared piece that I showed you guys over here. All right, so those are all equivalent pressure, measures of pressure, and they're all going to be used in equivalencies that you'll do for these kinds of gas problems. So let's talk about this funny one, this millimeters of mercury, and see where that comes from. Let's imagine you have this strange situation here. What I have right here, this tube, is a narrow glass tube that I've inverted into a pool of mercury. So right here, this is mercury. Whoops, let me change that to a different Hg, mercury. And I filled it entirely. This tube, I had it right side up moments ago. I filled it entirely with mercury. I held my finger over the bottom of it and inserted it into the pool of mercury. So the whole thing was filled with mercury. This is not unlike what you did. Oh, no, you guys haven't done that lab yet. So anyway, so you could imagine this thing is filled with mercury. Now, that column of mercury that you see rising up there is going to be held in place because of the atmospheric pressure pushing down on it. But of course, we have the counteracting force of gravity pulling it down. So what's going to happen is this whole thing will look a little bit different when if I let it sit for a little bit. So if I let this sort of sit and settle, what happens is the gravity and the pressure equilibrate. Now keep in mind that the pressure is pushing down on this mercury, and what that means is it actually is pushing upwards ultimately into this tube, causing that tube to rise up. So if I were to increase the downward pressure of the green arrow, it would actually lift the column of mercury upwards in that glass tube. Understand that? And what we have going on here is this space right here is a vacuum. There's no air in this thing. It's just being, as the column of mercury pulls down because of gravity, it leaves nothing in that space just above it. And if we were to then take a ruler, or actually more specifically a meter stick, and I were to, on a sort of clear sunny day, measure the distance that the column of mercury rose inside of that glass tube, I would find that it would rise to 760 millimeters, or 760 millimeters of mercury. And again, this would be equivalent to 1 atmosphere, or 101.3 kilopascals. All right? So that's where we get the 760 millimeters of mercury. On a day where we're going to have a high pressure zone, you would have a pressure, if it was higher pressure, right, pushing down on top of this mercury. It would raise the column a little bit higher, and instead of being 760 millimeters of mercury, it might be 770 millimeters of mercury, indicating a higher pressure. Now, pressure is a funny thing because, as I said, it's the force per unit area. But there are 3 ways in which you can mess with the pressure of something. So if you think of the black arrows as being vectors indicating the velocity, kind of like the velocity and mass of the particle as it hits against the wall of the container. The wall of the container is going to be this black thing right here. Okay, so let's just say this is inside of a glass bottle. If you have only 1 particle hitting against that wall versus having 6 particles hitting against the wall, you could imagine that in this first condition you're going to have relatively low pressure, whereas in here you're going to have relatively high pressure because you simply have more particles pushing against the wall. It's the difference between me holding a door shut against the wind versus having everybody in the classroom holding the door shut against the wind. We'd be able to exert far greater pressure even if none of us are doing any more work than we were doing when we were by ourselves, when I was by myself. But the collection of all of us holding the door shut is going to do a much better job of keeping the wind from opening up the door. In this case, oops, sorry about that. In this case, I've changed the velocity of the particle. So in situation 1, it's going to be coming at that wall of the container at a decent rate, but in number 2, it's going to be coming at a much higher rate. It's a larger vector showing that it's coming at a much faster rate of speed. And so as a result, it's going to exert more pressure. Again, it's the equivalent of me walking up to a door and pushing it versus running pell-mell at a door and knocking through that door, probably ripping it off its hinges because I'm so huge. And the last one to consider is the mass of the particle. Now, in the case of gases, this really isn't all that significant, but you can imagine in terms of solids, this could be a huge difference in terms of the mass. Even if you just take sort of a 10-pound block of cement lying on top of your chest versus a 2-pound block of cement, you're going to feel a huge difference in pressure there based on the mass of the particle. Again, it doesn't really come into play all that much with gases because they tend to be sort of, 1, solitary, and 2, relatively less dense than many metals that exist out there. It's not always the case, but it is for the most part. Okay, so one of the big things to consider is actually what I just said is why is it that gases keep their distance from one another? And why is it important that they not come in contact? Well, that's going to be something that we talk about later on, but I just want to introduce the idea to you with the idea as we step into the concept of what's called the kinetic molecular theory. And the kinetic molecular theory helps to explain not only the nature of gases, but the nature of the concept of pressure and temperature and volume and how they relate to one another. So let's start on that. All right, so we have a few givens associated with the kinetic molecular theory, and 5 of them to be exact. So let's go through those. You can see here that these are going to be sort of similar to the nature of gases. So we have here that gases have mass. Number 2, what I just referred to and alluded to moments ago, that there's lots of space that exists among the particles, which is a necessity here. Number 3, The particles are always in motion. Okay, number 4. And that is that particles collide elastically, both with each other and the walls of the container. Now, this is kind of an amazing thing to think about, one of those great things in science. Because when something collides elastically, it means that when it collides, it doesn't lose any of its energy, which is very different, say, from when your car hits the wall at 60 miles per hour. Once it hits the wall, all the energy goes into the wall and into the car, and hopefully not too much into you, and it dissipates as heat. Okay? In this case, the particles of gas, when they collide, they don't lose their energy. They have just as much energy. So imagine a situation where your car collides with a wall, but instead of losing energy as heat, it bounces off the wall at the same exact rate of speed, the same amount of energy backwards as it did when it was colliding with the wall, because that's exactly what's going on with particles of gas, which is kind of nuts. And the final of the 5 givens is that particles, these gas particles, exert almost no attraction to each other. And again, this is because they are so far away from each other and at such a distance that they don't actually sense the other particles around them. That may not seem important now, but you'll see that's going to be important later on. So with these givens, what does it mean? Well, this is where the kinetic molecular theory comes into place. And this is it. It's a very simple thing. When gas is heated, the kinetic energy of the particles increases. And as a result, if you increase the kinetic energy, if you increase the temperature, it increases the kinetic energy, but you can also flip that on its head, which is if you can somehow increase the kinetic energy of a volume of gas, then you can in turn also increase its temperature. But it's all based on the movement or the kinetic energy of these particles. All right, so take a moment to write that down. And again, one thing to keep in mind is that you can reverse this and go in either direction. Kinetic energy, an increase in kinetic energy leads to an increase in temperature, but also an increase in temperature leads to an increase in kinetic energy. And in the last 50 seconds, I want to talk to you guys about how we measure gases. There are going to be 4 ways in which we measure gases, and at this point, none of them are going to be too surprising given our lab and what I've been talking about today. Okay, so we have volume, which we measure in liters, temperature in kelvins, pressure in either atmospheres, kilopascals, or millimeters of mercury, and lastly, the amount of a gas, which we would measure in moles. Now, just to reiterate something here, Kelvin is equal to a degree C plus 273. And what's most important is kelvins are not something where you put the little degree sign next to it. It's just 273 K. That's it. Okay, speaking of that's it, that's the end of this screencast. Bye.